Hi. So good afternoon again. So welcome to the sharing about cellular network attack vectors. Thank you for coming. I hope to make your time worthwhile. Today I will share about 9 attack vectors which are unique to cellular networks. This will cover packet core and radio access network. I'm Salim. I lead the threat research for CTOne. I will outsource the detailed introduction to LinkedIn, so you're welcome to connect with me. Let's start with the cellular network end-to-end architecture. When we are in the range of a cell tower, our cell phone will connect to the antenna of the cell tower with radio waves. And the remote radio head in the cell tower will convert this radio signal to digital signal and forward to baseband unit. Now this baseband unit may be located near the cell tower, or more commonly, this may be located at a back office. So this baseband unit that converts the digital signals to IP packets and forward to core network. The core network may be connected to internet, may be connected to another base station, or connected to other core networks. So if we are sending a text message from line or WhatsApp, so the packet will be like from here all the way here and then goes to internet. And then the servers, the WhatsApp or line server reply back to the core network and goes back to the user like this. But if we are making just a normal call, there is no internet involved. So maybe just this way. So that's the basic architecture of any cellular network. So that leads us to the next section, the first section of the security sharing, which is about packet core. From that diagram, this is the place that we are going to focus on. There are, I will introduce 7 different attack vectors on packet core. For 4G and LTE, the packet core is also called EPC or Evolved Packet Core. For 5G, it's just called 5GC or 5G core. Let's take a little more detailed look at the packet core. It's not necessary to understand all the details in this diagram. All right. This part is the packet core. And what I want to show here is that the packet core is divided into 2. Control plane and data plane. The base stations are connected to both control plane and data plane. The control plane deals with signaling. That means when we power on the phone and the phone will connect to a provider, ISP. So this part is all handled by control plane. That is attachment, setting up a call. Those kind of things are all controlled by control plane. But when we use our phone or our device to browse internet or use data services, it will be forwarded, that data packets will be forwarded to user plane. Okay, so the control signaling is here, the data packets go this way. And one thing to remember is that for control plane, the protocol is NGAP, that is next generation application protocol. For user plane, all the user traffic, that means HTTP or call or whatever, RTP, streaming, everything, will be tunneled inside a UDP tunnel, which is called GTPU tunnel. So from this slide, we just need to remember that control messages goes here to control plane, and the user data goes to user plane. These are some of the attack vectors that we, couple of attack vectors that we spoke at Black Hat AMEA last year. In this one, an attacker in the internet can take advantage of the exposed interface in the UPF, and if the UPF has this flaw, the attacker can go directly to the connected devices, which is in the private subnet. That means these devices are actually having a private IP, which is normally not possible for attackers to connect. But if this flaw exists, the attacker can connect from the internet to the private IP subnet, and that's what makes this attack vector dangerous. This comes from Google Project Zero, where an attacker from the internet can make a voice over IP call and attack the baseband of the cell phone. This vulnerability was found in Samsung, some of the Samsung phones. The CVE is here. And for every attack vectors that I show here, there is a CVE or a reference. That's because I don't want to deal only with the theory. So you can see that these are all verified in at least one product, either commercial or open source. There are 3 more here. These are attacks on the packet core infrastructure from connected devices. That means we can use a cell phone to attack the packet core infrastructure. In this case, the attacker can send a GTPU. That means he already makes a tunnel, and he tunnels the user traffic or malicious traffic inside this tunnel. And like we saw before, between the base station and user plane, there is already a tunnel. So this will become GTPU in GTPU. And some implementations cannot handle this well, and this will bring the packet core, user plane of the packet core down. Now, some of you may be familiar with GTP in GTP attack. It's been around for a long time, but that GTP in GTP is actually GTPC in GTP. GTPC in GTPU, but here I'm talking about GTPU in GTPU. And in this case, this is a variation where the user equipment can send a control plane signal, but from application level. And this will be a tunnel in the GTPU, goes to the user plane, and if the user plane and the control plane isolation is weak, this packet can cross over to the control plane and crash here. So this is also a real case. We have already seen this in action. And the third one here is the attacker can use a SDR, software-defined radio. It costs about $3,000 to $5,000 USD, and directly send the baseband signals to control plane. There's a reference for that. So these two are actually application traffic, and this is actually control plane. So that's the difference here. Okay. 2 more for packet core. This is what we found on Microsoft Azure Private 5G Core, AP5GC. This is the ZDI number, CVE number. In this case, the attacker impersonates a base station, but actually that's only towards, the impersonation is only towards this side. It's not a fake base station. The attacker just sends some malicious or anomalous signaling packets to the AMF, that's control plane, that can bring the AMF down. And this is verified in several packet cores. And this one is a recent disclosure about SCTP quantum insert. Some of you may remember TCP quantum insert from the old Snowden leaks. It was alleged that it was used by NSA to do something. Anyway, SCTP quantum insert is a port of TCP quantum insert. In TCP quantum insert, what the attacker will do is that the attacker will try to send RST packet, reset packets to TCP connection and try to reset it. In SCTP, it's the same. The attacker will try to send SCTP abort packets to cut existing SCTP session. But in my opinion, this is not very easy to attack, not very easy to execute, because the attacker needs to know the sequence number of TCP or SCTP. So while this is a theoretically good attack that is possible, but not very easy to really execute. However, if the same infrastructure is shared by different networks, this will become important. We have verified, these are some of the CVEs and 0 days we filed on different packet costs. Though all these attack vectors that I mentioned have been verified in different packet costs. Some of them are commercial, like Nokia CMU or Microsoft Azure, and there are others. And some are in open 5GS, free 5GCs, they are open source. Then why do we use open source? Because there are many commercial products based on open source. And besides, we don't file all the vulnerabilities we find on open source as a CVE. We only file attack vectors, not attacks. For commercial products, we file for both attacks and attack vectors, but for open source, we just focus on attack vectors. Like I said, GTP in GTP is known for a long time, but until now, this attack has been limited to sending one packet, one connectionless packet to the GTP tunnel. But we have a new tool here. It's very difficult for an attacker to execute advanced attacks if he can only send one packet. So for advanced attacks, and if an attacker wants to use Metasploit or Nmap or something like that, he needs to be able to establish a two-way connection with the connected devices. And that's what this tool will do. It will weaponize tunnel injection. And we have also filed a patent for this. These are some of the research papers that we published on packet core. This is about, this takes the example of the Nokia CMU packet reflection vulnerability, and these two are about open source attacks from user device to the infrastructure. Now, some of you may have this question: have we seen these attacks in the wild? Are these attacks already exploited? The short answer is no, we don't have data for that. But the long answer is we wouldn't know until it is really done, because these are DOS attacks. The cyber criminals are motivated by money. They don't really use DOS attacks. They prefer ransomware or such attacks where they can make money. DOS falls here in the sabotage. They only constitute 5% of the total attack space. So this sabotage will come into picture only in times of conflict or war, like the case of Ukraine and Russia. For telecommunication and critical infrastructure, the main motivation of attacker is espionage. That means spying. For both espionage and sabotage, the common characteristic is that the attacker needs to hide for a long time. For espionage, the attacker needs to hide and steal data. And for sabotage, the attacker needs to hide and wait until the time comes. There are a few APTs that target telecommunications, and some of them have also developed tools that are specific for cellular network protocols. One of them is red mention. One of the tools they use is BPF Door. BPF Door is a clever backdoor. I will explain it later. And BPF Door has a new, recently discovered variant called GTP Door, where the attackers use GTP packets or cellular communication protocols to hide inside packet core infrastructure. You may remember that Light Basin is another APT that has been in the news for a while. They also have similar packet hooking structure as BPF Door. Why is BPF Door important or clever? Because mainly BPF Door has two components. One is here, which it will listen to all the packets that pass through the Linux stack. Listen here and trigger the implant if it sees a magic packet. This is clever because many of the firewalls in Linux is hooked to NetFilter. But in this case, BPF Door is before NetFilter, so no matter the firewall see the packet and drop the packet, it's too late. The implant is already triggered here. We move to connected devices. I will take the example of a water treatment system, water pump and purification system. This is an example of a reference architecture from Advantech Web Access. As you see, here is a centralized management console, and the water pumps are connected to the centralized management pump via a LTE router. So an attacker can target at least two places. One is attacker can target this place, the management system, or attacker can target the router. This is another reference architecture of water purification system from Moxa. In this case, they say that the sensors are deployed all along the water pipe systems, and these sensors will feed back the amount of impurities or chemicals in the water to the management system, and there if the level of chemicals is more, they can adjust the process. The architecture is similar. There is a central management process and there's a router. So if we take this reference architecture and extend it to general industrial architecture, it will look like this. We have connected devices here, and they have a controller, and maybe they are connected through a router to a base station, and maybe they are connected through public infra to 5G core in the ISP backend. How can the attacker attack it? One way is to attack the IoT cloud, the management system. Another way is to attack the exposed interfaces in any of these devices. And another way is to use the tool that I just mentioned, along with Metasploit and MAP and such attack tools. Maybe it goes to the router or it goes to the controller first, and from the controller it can reach all the connected devices. So let's move on to RAN. This is the part we are going to talk about. Baseband unit. Now, baseband units have evolved. Originally, the baseband unit was co-located with the radio tower, but then the baseband unit moved back far away from the radio tower and maybe in the back-end office. And when it comes to virtualized RAN, the first thing is the whole baseband unit is virtualized. And the next step is that it was disaggregated. That means the baseband unit was divided into CU, that is central unit, and a distributed unit. However, at this point, CU and DU communicate with closed protocol. That means still proprietary. Although they are virtualized and disaggregated, they still have to use proprietary protocols. When it comes to Open RAN, this communication interface is open standard. So the CU can come from one vendor and the DU may be coming from another vendor. And there is also a new component called RAN Intelligent Controller that adds intelligence to the RAN system. So how does RAN Intelligent RIC add intelligence? For that, there are accepts. we can think of XApp as third-party applications that do certain advanced functions by taking advantage of their position in the RAN. They can control, they can automate, they can allocate radio resources based on the feedback, based on external, based on machine learning. So this is how RIC adds intelligence to RAN through the XApp, through third-party XApp. There are so many third-party vendors developing all kinds of XApp. For example, vehicle V2X, vehicle to everything communication, and so on. So XApp have become quite important in this architecture now. So we collaborated with Taiwan's university, NTUST, on researching this Open RAN architecture, and we found many vulnerabilities. I will explain two of the vectors, attack vectors that we found in Open RAN. One is that the internal messaging architecture of RIC is not clearly defined, so it is implementation dependent. So we found that the route RMR, the RIC message routing protocol, and the implementation is very vulnerable, and it can bring the RIC down. So this is one attack vector where the XApp compromises or XApp attacks the RIC, a third-party XApp attacks the RIC and brings it down. And this one is the third-party XApp takes advantage of privileges and attack the RIC component using a non-authenticated or leveraging the lack of authentication in some of the HTTP APIs. So there are at least two attack vectors here. These are some of the couple of papers that we published on Open RAN security. And we also went for academic publications because we wanted to make sure that we are on the right direction. We wanted the best experts in the industry to review our work. And here are the results. We had two IEEE papers, a conference and a journal. These are the details of the attacks, but I will not go into the details of it. If you are interested in this, please attend the session by my colleague on Thursday. So we also developed a malicious XApp that can execute at least 6 attacks. So ORAN SC is open source. So why do we choose ORAN SC? It is a reference architecture, and as you can see that almost all top vendors contribute to ORAN SC. So it's very likely that at least some of these vendors use some of these vulnerable components in their commercial products. So these attack vectors that I just described, we have also contributed to MITRE FIGHT. FIGHT is the MITRE framework for threats for 5G. In this diagram, there are like Discover TEID, uniqueness, network boundary bridging. There are several places where we have contributed to. So these attack vectors are all included in many of these TTPs. And our contribution, the things that we have I just described have been recognized by MITRE as well. So with that, we come to the end of this presentation. Do you have any questions? If no questions, thank you.